Okay, let's recap statistical inference for the difference in means when sigma 1 and sigma 2 are unknown but assumed to be equal. So we know we have these two populations and we're wanting to perform statistical inference. That is, we're wanting to either find a confidence interval or we're wanting to do some hypothesis testing for the difference in means of those two populations. Okay? And we know that the sampling distribution for the difference in means, okay, so we have two populations, 1 and 2, and this is the distribution for the difference in means. It's the sampling distribution, so we've got these sample means for these two populations. We know two things. One, we know several things. One, we know that the mean of this distribution is mu1 minus mu2, okay? And we know that if we don't know what the standard deviations are for the two populations, if we don't know sigma 1 and sigma 2, but if we assume that they are equal, then the standard deviation of this thing we assume to be a pooled standard deviation. Okay, pooled standard deviation is just a way to calculate the sampling distribution, the standard deviation for this sampling distribution. And this standard deviation would be the square root of n minus 1 times s1 squared plus, that's n1 minus 1, n2 minus 1 times s2 squared all over n1 plus n2 minus 2. Okay? And we multiply that by the square root of 1 over n1 plus 1 over n2. Okay? That would be our standard deviation of the sampling distribution for the difference in means. Okay? And we know that this distribution is a normal distribution if population 1 is normally distributed and population 2 is normally distributed, or if we can apply the central limit theorem. And that is if the sample sizes that we pull from population 1 and population 2 are both bigger than some number, let's say 30. Okay? So we can assume this is a normally distributed sampling distribution if either population distributions are normal or if we collect a sufficiently large sample size. It has mean mu1 minus mu2, and this is the standard deviation. Note that it contains s's, not sigmas. Okay? It contains the variance for the sample variance for population 1 that we pull from that sample from population 1, and the variance of the sample that we pull from population 2. Okay? Since we're not using sigma 1 and sigma 2 here, our confidence interval is going to contain a t statistic. Okay? And so what would that confidence interval be? What we're doing here is we're finding a confidence interval for the difference in means. Okay? So we've got a point estimate for the difference in means. Okay? y1 bar minus y2 bar, that's a point estimate. To that and from that, we're going to add and subtract a margin of error. The margin of error is a function of three things: variability, sample size, and confidence. Okay? On my chest, I have a tattoo of William S. Gossett, and underneath that, it says variability, sample size, confidence. So this margin of error is going to be t. For our particular degrees of freedom, alpha over 2, times this thing, okay? n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared all over n1 plus n2 minus 2. And we're going to multiply that by 1 over n1 plus 1 over n2. Okay? This is the confidence interval for the difference in means. It's going to produce some lower bound and some upper bound. And inside that bound, inside that set of bounds, we think mu1 minus mu2 really lies. Okay? If both of those bounds are negative, then mu2 is bigger than mu1 with some amount of confidence. If both of those bounds are positive, then mu1 is bigger than mu2 with some amount of confidence. If we have a negative lower bound and a positive upper bound, then we can't really draw many conclusions about whether one is bigger than the other, because the confidence interval contains 0. So there's some likelihood that the difference is 0. That is, mu1 and mu2 are equal to each other. What is our degrees of freedom here? Degrees of freedom are n1 plus n2 minus 2 for this case. Okay? And again, this case is where sigma 1 and sigma 2 are unknown but assumed to be equal. Okay? So this is the confidence interval portion of statistical inference. Now let's talk about the hypothesis testing. Okay? As always, we have 3 different kinds of hypotheses that we could be addressing here. One is that mu1 is equal to mu2. Okay? The mean of population 1 is equal to the mean of population 2. We could rewrite this as mu1 minus mu2 equals 0. Just put this on the other side. You got negative mu2 on the other side, and you have 0 left over here. Okay? These two are equivalent statements. Alternatively, we would have the contradiction of the null hypothesis, which is this, rewritten as mu1 minus mu2 not equal to 0. Equality must always be in the null. We know this. This doesn't change whether we're dealing with one population or 2 populations. Equality is always in the null. So we have the equality statement here and the contradiction statement there. Okay? So we could address this kind of set of hypotheses. Okay? We could also, instead of 0 here, we could put a value d naught. Okay? We could test if the difference in the means is some number. Okay? Is it 0 or could it be 3.5? Okay? We could insert whatever number that we're interested in determining the difference in this blank right here. Okay? Just like the other situations, we have equal to, not equal to, or we could have greater than, equal to, and less than in the alternative, or we could have less than or equal to, greater than in the alternative. Okay, same kind of idea, variations on a theme, right? We've learned all this stuff already. It's just there's a slight variation on how we do the confidence interval, a slight variation on how we do the test statistic. Okay, it's a t-test statistic, and it is y1 bar minus y2 bar. Okay, the difference in sample means. How different is this difference from the hypothesized difference? Okay, and that's why we rearrange this kind of hypothesis to something that looks like this. We put this number right in here. Okay, so how different is our sample evidence from our hypothesized situation? That's something that we want to answer here in standard deviation units. And these are our standard deviation units. Okay, n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over n1 plus n2 minus 2. We multiply that by 1 over n1 plus 1 over n2. Okay? And this is our test statistic, right? How different is the sample evidence from the hypothesized situation in standard deviation units? If this is different enough from this, then we'll reject the null, because our test statistic will lie in whatever tail that we're interested in. Okay? And those tails, again, this doesn't change from what we've talked about previously. This situation is a 2-tail test. If we have strictly equal to, strictly not equal to, we have a 2-tail rejection region. Okay? We just find the value on the t-axis associated with our particular degrees of freedom. Okay? Alpha over 2 in each tail. Same kind of idea as it's always been. Here, for this situation, we have a lower tail test. Okay? All of alpha is going to be in the lower tail. It's going to be a lower tail rejection region. Up here, we have greater than in the alternative. So we're going to have an upper tail rejection region. Okay? So if the test statistic falls in the rejection region, we reject the null. That means that this is different enough from this in standard deviation units that we should be rejecting this null hypothesis of equality. Okay? So these combined, the confidence interval and the test of hypotheses, those combine to form this notion of statistical inference. taking a sample and inferring about the larger population based on that sample. So we could address problems of either type, confidence interval or hypothesis tests, and we'll do a few of those examples here coming up.